So this is the second day of talking about chapter 10, and we're thinking about liquids and solids, and we're actually really spending a little bit of time to make sure that we understand the impact that intermolecular forces have. So it's essential that we cover this topic because probably more than any other topic that we cover in general chemistry, intermolecular forces have huge implications for biology, for physics, for chemistry, as really any of the sciences. And you can see its application in computer science, in virtually all of the career fields that you might be considering. So I think this is a really important topic. What's also really interesting to me, especially as we think about this, is two pieces, right? So some of our challenge is how we represent this information. And so this is really where you have a lot of choice. So this kind of gets back to the ownership and agency piece. You might be more comfortable taking notes, writing out words to describe intermolecular forces. Or maybe it's something where an actual diagram or a visual representation of what those forces look like might be something that's more accessible to you. Or maybe you're better off, calling up your best friend and actually talking them through an explanation of the difference between condensation and vaporization. So some of this is really your choice in terms of what's the best fit as you explore these topics. And I think that having that sensitivity to what are the best strategies for you personally to learn is really what the idea behind ownership and agency is all about. So it's giving you the freedom to make choices about what makes the most sense for your learning. We've talked about these 4 science practices every day since we've started the semester. And hopefully at this point in time, as you're going through and working through problems, whether that's in class or in discussion or with Alex, you're being mindful of when maybe you want to ask a question or when it's appropriate to analyze or interpret data. And I think that some of that is just the business of how we do science. So it's the way you would approach solving any problem. I think if you're stuck, right? If you come to a problem and you're like, oh, I don't know what to do about this problem, or I don't know how to solve this problem, thinking about which one of these strategies might be a place where you want to start is a great way to approach an unknown. Okay, we left off last time talking about the difference between intermolecular forces and intramolecular forces. And I think the most important piece to remember here is that inter is between 2 molecules. Arlene had this really great way of referencing it, right? The interscholastic, so between 2 schools, right? So Duke basketball playing Cal State LA basketball versus the intramolecular, which might be 2 teams at CSUMB playing basketball against each other. So intra is within 1 molecule, inter is between molecules. And it doesn't have to just be 2. Intermolecular forces could be 10 molecules or 20 molecules. It could be many molecules. So that's probably one of the most important distinctions that we need to make, is that it's always between molecules, whereas intramolecular forces are within. I had someone ask a question as a follow-up on Tuesday, and they were like, well, how does that change, like, as you get farther away? And it was a really astute question, because the force that something experiences is entirely dependent upon distance. And so while it's outside the scope of this class, there are actually mathematical equations that specifically relate the distance between 2 objects, and that distance, right, determines how strong the force is. That's not something that you're going to be asked to calculate for this class. It's not something you're going to have to do on a final, but it's something that in a later course, or maybe, say, for example, in physics, you might encounter. We also talked briefly about the difference in terms of the strength of forces. So London dispersion forces being the forces that virtually all molecules experience, because any molecule can induce a dipole in any other molecule. And so these are very weak forces, but they're present almost everywhere. And then we talked about how the next strongest forces are dipole-dipole interactions. This is where if I have a molecule that has a partial negative or a partial positive charge because of the difference in electronegativity, I'm going to see differences in the way that interacts. And then we talked about hydrogen bonding. The one we really haven't talked about is ion dipole, and that's mostly because if you have something that is ionic and has charge, it's going to interact with a partial charge, similarly to a dipole-dipole, but because there's an ion involved, it's going to be a slightly stronger interaction. And then this is all relatively new knowledge for us, but we have a fair amount of prior knowledge with forming both covalent bonds and ion-ion interactions. So those are the different types of forces that we're taking a look at in chapter 10. Intriguingly, there are some really cool physical properties that result when we're thinking about intermolecular forces. I think for me, the one that always stands out is capillary action, because I've always wondered why there's a meniscus that forms that is concave versus the meniscus that you see for mercury that's convex. That always just looks so strange to me. And the reason for that is because we have adhesive forces that are attracting the molecules within the tube, both to each other and to the surface. And so we have adhesive that is to the surface, but then we have cohesive forces, and those are the forces that attract liquid molecules to each other. And so if I have a narrow enough tube, then these two forces are going to draw liquid up the tube. And I think that's so fascinating because it's not that a meniscus doesn't exist, say, for example, in a beaker. It's just that we really don't see it because that tube is wide enough that the meniscus is pretty shallow. And I suppose if you had an infinitely wide beaker, then maybe you would have no meniscus at all. But in reality, most of what we see, say, for example, in a glass or in a test tube, are these adhesive and cohesive forces pulling on liquid molecules. So that's just a quick recap of an example of the physical properties that result from intermolecular forces. So today we're going to start thinking about phase changes. This is something that we've actually already seen before. You have some prior knowledge here. So in the chat box, we'll do a modified KWL. Tell me what you remember about the phase changes that we see here. So you've got 6 to choose from. We'll have some variation in terms of responses. If we get some of the same topics, that's okay. It'll just be a reminder that those are things that we remember really well. So tell me what you know about phase changes. Choose one of the following topics and tell me a little bit about what you know. And if you're like, ooh, I don't remember where to find the chat. If you look in the bar and you click on more, there should be spaces for you in terms of being able to do the chat. Oh, great. Thanks, Megan. So Megan said freezing is going from liquid to solid. Marcus said water can change to almost anything. Excellent. That's a great observation. Oh, I like Arlene's observation too. When I find old liquid food in the freezer and it is smaller than I remember, some of the liquid sublimated to gas. Amber shared that condensation is an exothermic reaction. Madison shared that sublimation is when it goes from a solid to a gas. Hope shared that vaporization is from liquid phase to vapor phase. Oh, that's awesome. That's fantastic prior knowledge. So if we're thinking about those pieces, right? So Mackenzie's sharing that sublimation and deposition skip the liquid. A great example of that would be dry ice. So as we're thinking about each of these terms, our phase change really is a transition. It's a transition from one phase to another phase. And isn't it interesting if you think about this in terms of kind of the pattern? So for example, fusion, right, is going from a solid to a liquid. Freezing, right, is going from a liquid to a solid. So for me, I always remember that the pattern is the 2 F's when I'm thinking about solids and liquids. And then I pair vaporization and condensation together. So vaporization is going from a liquid to a gas. That's like if you were boiling water and it was becoming steam. And then condensation is going from a gas to a liquid. So if you, say, for example, have a glass of ice, it's the water vapor that's condensing on the outside of the glass that then forms those water droplets that roll down the side of the glass. And then the last pairing is sublimation and deposition. This is probably the one that folks are less familiar with because we don't talk about it as often as we talk about vaporization and condensation or fusion and freezing. But sublimation and deposition is what Mackenzie described. That's going from a solid to a gas or a gas to a solid and skipping the liquid phase. And so if we think about those patterns, this is probably the one that you're less likely to see kind of in common everyday life, because usually when we think about sublimation or deposition, there's some really specific conditions that we need. For example, you can actually see here that it's a test tube within a test tube. So my top test tube has ice in it. My bottom test tube has solid iodine. And so as my iodine goes from 80 degrees Celsius to cooling to 0 degrees Celsius, I observe sublimation, or the formation of iodine solid on the outside of this test tube that the inside has ice. So if I think about this, it's a solid transitioning directly to a gas phase. So a good way to think about that is maybe dry ice smoke that you sometimes see as special effects. And then deposition would be when a gas transitions directly to the solid phase. And this is the example that we have here. This is iodine, where the gas I2 is transitioning to solid I2 crystals that are depositing on the cold surface of the ice finger that's shown here. So these are examples of phase changes, and you can imagine that the reason these occur is because of energy. So you either have something that's giving off energy or taking energy, and that's what we're going to be looking at today. So the first example is probably one you're very familiar with, even though you don't necessarily think about it all the time. And that's the heat of vaporization. So this is the energy that is required to vaporize 1 mole of a liquid. And if you think about the energy or the heats that we've studied before, those are typically in kilojoules per mole. That's a unit that's going to be really familiar to you, both from what we've studied in terms of thermochemistry already, say, for example, Hess's law, or studying the heats, say, for example, when we had water in a metal, or we had the transfer of heat from cold water to hot water. We typically measured thermal energy in kilojoules per mole. So it makes sense that it would be dependent upon temperature. And here's the piece I think that's super interesting. The heat of vaporization is always positive. That's because vaporization is endothermic. So that means I'm putting energy in. So I'm always adding energy to or putting energy in, which is why my delta H is positive. I'm not giving off energy, I'm always putting energy in. Condensation, on the other hand, is exothermic. That's giving off energy. So we use these terms endothermic and exothermic. They're going to be really important academic language for you to be familiar with. So for example, you might talk about endothermic or exothermic reactions in a biology class, say for example, Bio 210. Or you might talk about endothermic and exothermic reactions, say for example, in studying muscle fibers, or the use of ATP to drive movement. And then we often will talk about the heat released by condensation of 1 mole of gas as negative delta H vaporization. So if we think about it, our heat of vaporization is going to be positive because it's endothermic. The heat that is released by condensation will have a negative delta H. So thinking about those signs again is going to be really helpful for you as you make sense of the difference between endothermic and exothermic. All right. So let's take a look at a problem. In your notes or on your whiteboard, in a hot climate, you can lose up to 1.5 liters of sweat in a day. If you're like, wow, I'm not sure I have a visualization for that. Think about a 2-liter bottle of soda, right? The ones that are, right, kind of roundish shaped, right? Think about that being, right, almost full. So 1.5 liters of sweat a day is a lot of water. How much thermal energy does it take to vaporize that much sweat? Assume that the sweat has the same density and heat of vaporization as water. So my delta H of vaporization for water at 37 degrees Celsius is 43.46 kilojoules per mole. So if we think about the information that we have in this problem, we're given a volume and we're given our units of heat of kilojoules per mole. They gave us a clue where they said, assume that sweat has the same density and heat of vaporization as water. So take a moment and think about how you might set up and solve that problem. And if you're not sure, that's okay. Go ahead and take a moment to write down your givens and think about the relationship between the information that's available in the problem and what you're being asked to solve for. So there's a couple of pieces of information you need to kind of pull out of that problem. So the first is, right, this 1.5 liters of sweat in a day. We typically think of the density of water in grams per milliliter. So probably the first step that you might need to do is convert your liters to milliliters so you can cancel these two units. If you're not sure how to do that, remember that there are 1,000 milliliters in 1 liter. But we'll start here. So if we have 1.5 times 10 to the third milliliters, right, that's the volume of sweat that we have. And it said sweat has the same density. So we're using the density of water, 1 gram per milliliter. So now our milliliters will cancel and we're left with grams. Well, we know the molar mass of water, that's 18.02 grams. So now our grams cancel. That gives us 1 mole of water. This is exciting because now we have a unit, moles, that shows up, right, in our delta H of vaporization. So now we know that if we multiply by 43.46 kilojoules per mole, now our moles will cancel and we'll be left with kilojoules. So if you think about your dimensional analysis, you're going to multiply across the top, divide by what's on the bottom, and that's going to give you 3.6 times 10 to the third kilojoules. If you think about that, that's a fair amount of energy that you would have to expend in order to generate that much sweat. Critically, you'd want to be mindful of the fact that if you lose that much sweat in a day, you definitely want to rehydrate because that's going to be a significant loss of water for your system. I think when you are approaching this type of a problem, if you're not sure what to do, one of the best things you can do is think about the information that you're given and if there are any other units that you could use to represent that information. So for example, converting liters to milliliters is really what allows us to get this problem started because we know that our density is in grams per milliliter. Now there's another way that you could have solved this problem. You could have converted your density to grams per liter. Right? It would have been the same outcome in terms of solving the problem. Then you could have used 1.5 liters of sweat in a day with your density in grams per liters. That would have been a totally acceptable way to solve this problem too. So part of what I hope you see is that there are multiple ways that you can approach solving these problems, especially when it comes to manipulating units. Okay. So if we're thinking about the heat of vaporization, we're going to use this word volatile. So volatile means that liquids vaporize easily. Can you think of any examples of volatile liquids? If so, can you put them in the chat? what's something that vaporizes easily? What's something that, say for example, if it spills, rarely stays as a liquid for long? What are some examples? Can you think of any? On a hot day, water does not stick around long. Yep. Acetone is definitely volatile. Gasoline, those are great examples. Yep. So I think your examples showcase the following. It really depends upon what conditions your environment is. So, for example, on a cold day, I'm not going to vaporize water, but on a hot day, I certainly would. It doesn't really matter whether it's a cold or hot day. My acetone is going to be gone, right? If you spill acetone, say for example, if you were in a lab and you were using acetone as cleanup and you were rinsing out a flask and you were to spill some drops in the hood, that acetone would be gone before you could get the paper towel to wipe it up. Rubbing alcohol is another example. Thanks, Claire. And Deja, absolutely. Gasoline is definitely something that is a volatile liquid. So here's the question. Why? Why are they volatile? Well, it's because they have weak intermolecular attractions. And so let's take a minute and think about what we know in terms of intermolecular forces. So which of these molecules would evaporate most quickly at the same given temperature? So if I had a cup of each of these molecules out, let's say for example, it's a warm day, so it's like 80 degrees, which one would evaporate most quickly, do you think? Take a minute and come up with your prediction. Most importantly, in addition to your prediction, say for example, I predict that ethanol will evaporate most quickly at a given temperature. Think about what your reason is for that. Why is it that you think ethanol would evaporate most quickly at a given temperature? Take a moment, think about what your prediction would be, and then think about what your reasoning for that prediction is. We're going to take a look at rates of vaporization. So the rate of vaporization increases with decreasing intermolecular forces. So the weaker my forces are, the faster something will evaporate. So if we're looking here, let's take a look at our curves. So ethyl ether is the curve here in red. Ethyl alcohol is the curve in yellow. Water is the curve in blue. Ethylene glycol is the curve in purple. So let's go back for a moment and think about what we know about the structure of these molecules. So let's think about diethyl ether for a moment. What are the intermolecular forces involved with diethyl ether? So if you're looking at this molecule, you're probably thinking, well, it has London dispersion forces because it has carbon-hydrogen bonds, and I know those have London dispersion forces. And you're like, well, it has an oxygen molecule and it has a hydrogen molecule, so maybe it has dipole-dipole forces, and maybe it can do hydrogen bonding. But interestingly enough, because of the structure or the shape of this molecule, it's actually very difficult for diethyl ether to form hydrogen bonds. Essentially, it is something that, depending upon the position of this oxygen, is really what determines its formation of hydrogen bonds. But let's look at some other examples. So let's look at ethanol. So ethanol has this OH, and right, if we're thinking about its intermolecular forces, it's definitely going to have London dispersion forces. Because it has a difference in electronegativity, you're going to see dipole-dipole forces. But this one, because it has OH, is definitely going to be able to form hydrogen bonds. But it has this other side of the molecule that maybe creates a little bit of steric hindrance. It kind of blocks, right? I would only typically be able to form hydrogen bonds if I approached from the right-hand side of the molecule. If I approach from the left, that might be harder. Water forms an incredible number of hydrogen bonds because it's small, And essentially, it's the equivalent of 2 hydrogens that are available as well as an oxygen. So water is phenomenal at forming hydrogen bonds. Ethylene glycol, right, is going to form the most hydrogen bonds, though, because there's actually 2 OHs on this molecule. And it's relatively small, so it's able to form multiple hydrogen bonds because it has 2 OHs. So if we go back, right, we can take a look at the curve. Now, I think it's really important here, right? If you made a prediction and that was wrong, that's okay. Scientists make predictions that are wrong all the time. The only way you'll know if a prediction is wrong is if you could test it. And so let's say, for example, you predicted that ethylene glycol was the one that would vaporize most quickly. Well, when you would go into the lab and do your test, you would be able to say, oh, look, the data shows that my prediction was not correct. Great. That's wonderful information. Having a negative test can be really valuable. Being able to know that one prediction is not correct just means that then you have the opportunity to make another prediction, right? And right, maybe that one will also be incorrect. I think that sometimes we operate under the assumption that brilliant scientists always make the right predictions, but nothing could be further from the truth. In fact, some of the most significant scientific discoveries that we know of are because a scientist made a prediction and it was wrong. What they thought would be the case was not in fact true. So be encouraged, right? It's much more valuable for you to make a prediction, test that prediction, and then iterate your thinking than it is for you to never make a prediction at all. Because it's only by taking that risk and thinking, oh, I think this is what might happen, that you'll then be able to test and prove to know whether or not you're correct. So if we're looking at this diagram, the takeaway, the most important for you is that pressure and temperature are what are going to influence, right, the behavior of our phases. So if I want to know how something is going to go from a liquid to a gas, right, I'm going to be mindful of the temperature that that liquid is at. And then, right, I'll be able to say something about the pressure or the behavior of those molecules based on where I would find that temperature. So we said at 80 degrees, right? So that's a pretty warm day. So if we're thinking about that, right, even on a very warm day, I'm not going to see a lot of vaporization of ethylene glycol. It's going to stay a liquid. I will see some vaporization of water, but both ethyl alcohol and ethyl ether will vaporize very quickly. In fact, my suspicion is that literally as soon as you drop that droplet, it would vaporize. So when we think about the rate of vaporization, it's dependent upon the intermolecular forces. Okay, so let's talk for a minute about vapor pressure. Vapor pressure is the pressure of a vapor or a gas in dynamic equilibrium with its liquid phase in a closed container. So what do we mean by closed container? Well, I want to show you a really cool PhET simulation. So here we have a closed container. It's closed in the sense of there's really no way that the gas molecules can escape. So an open container would be an example of something like a glass. A closed container is something that we see here. And I want you, you'll have the opportunity, this is in your virtual learning plan if you want access to this simulation. But there are a couple of things that we can do. So for example, in a closed container, we can add heat and we're gonna see a change in the behavior of our molecules. So for example, the molecules that were a liquid, once you add heat, are eventually going to have enough energy that they can escape that liquid and become free moving molecules such as what we see here. If I were to cool my closed chamber, what do you think will happen to the molecules? What do you think will happen to them? Notice what's happening to the pressure. My pressure is dropping. And eventually, if I cool it sufficiently, it will become what? Yep, they'll essentially cool to the point where it becomes a liquid. Those intermolecular forces between molecules are in play, right? And they, right, can change phases. What if instead of neon, let's say I chose water? How do you think your water molecules will behave differently than your neon molecules? So let's go ahead and do the same exercise. We're going to add heat. What do you notice? I wonder what it is that makes the water molecules spin the way they do when I add the heat. So I think in this instance, I have to add enough heat because I am going to constantly be breaking the hydrogen bonds that form between water molecules. So let's say I'm going to cool this then. What do we think will happen if I'm cooling the molecules? Again, notice my pressure increases when I increase my temperature. When I'm cooling, my pressure is going to be decreasing. And we'll talk about this in just a little bit, but one of the things that you can do here as you're exploring the behavior of these molecules is you can actually look at the phase diagram, which will tell you precisely the temperature and pressure at which you'll see the transition between, say, for example, liquid and solid or solid and gas. So this is a really great resource for you. It'll be something that you'll use in the future as you're solving problems. It's a great simulation to help you make sense of the phase changes. So coming back to this idea of vapor pressure, if I think about the vapor in dynamic equilibrium, so remember equilibrium is the exchange where the rate of exchange is the same between, say, for example, liquid and gas and liquid. That's what vapor pressure is. So it's the exchange or the pressure at which liquid and gas molecules exchange at the same rate. So then if I think about this for equilibrium vapor pressure, if I have, say, for example, something that is a closed vessel, initially there's no condensation. And then once I get some H2O, oh, sorry, I need to lower this. Then there will be some condensation that occurs. So notice, right, I have water molecules rising up. Those water molecules are now in the gaseous phase, but they can exchange and condense back down into the liquid phase. And so a dynamic equilibrium is where the rate of evaporation, so the rate at which a molecule escapes the liquid to become a gas, and the rate at which a gaseous molecule returns and becomes part of the liquid, it's where those two rates are equal to each other. So when we think about equilibrium vapor pressure, we're saying that at this pressure, the rate of exchange is the same between a liquid and a gas. So let's take that then and apply it to something that we know. We're going to talk about boiling point. Specifically, we're going to talk about normal boiling points. The boiling point of a liquid is the temperature at which its vapor pressure equals the external pressure. So if you're thinking about this from practical context, think about if you were boiling a pot of water, the temperature at which the vapor pressure of the gas molecules will equal the external pressure. So we know that boiling depends on pressure. If you recall, you guys did a really excellent claim evidence reasoning statement talking about how the temperature at which you would need to boil something would depend upon its altitude. And that's, again, because of the pressure of our atmosphere. So the normal boiling point of a liquid then is the temperature at which its vapor pressure equals 1 atmosphere. So the normal boiling point of a liquid, say for example water, is the temperature at which its vapor pressure equals 1 atmosphere. So if you're at sea level, this is the temperature that it would take to boil water. So at lower pressure, water is going to boil at a lower temperature. So if I add heat to boiling water, it's not going to increase its temperature until all of it is vaporized. So if I'm looking at this diagram, part of what I want you to notice is that there's an increase in the heat until we start boiling, and then the temperature stays constant even though you're adding more heat until all of the liquid molecules have become gaseous molecules, and then the temperature will rise again. So if you think about boiling a pot of water, it's pretty rare that we do this, but let's say you had a pot of water on the stove, you're adding heat. At the beginning, when you're putting the pot of water on the stove, it's not boiling at all. But as you add heat, right, you start to see bubbles form, right? And by the time, say for example, you've reached 100 degrees Celsius, you probably have a rolling boil. But you could watch that and measure its temperature, and it would stay at the temperature of 100 degrees until all of the water molecules had escaped to become gas. And then if you had, say for example, an infrared thermometer, you could actually measure the steam. And if you were able to do this in a closed system where you could measure it, that steam would also continue to increase in temperature once all of the liquid had become gas molecules. So if we think about that then, and we think about the role of pressure, if we're going to cook at high altitudes, it's going to take longer. So this is, I think, one of the reasons why if you're up in the mountains, right, your baking times or your cooking times might be different than if you're cooking at sea level. So if we go back then and think about our vaporization pressure, one of the things that we can notice from the graph that we looked at before is that our temperature is going to increase exponentially. So these are curves, right, that start low but go high really fast. And so if you think about the exponential nature of pressure vaporization, right, as you increase temperature really quickly, the pressure increases. All right. So with those kind of big pieces in mind, we're going to work on solving one more type of problem. So these are Clausius-Clapeyron equations, and they are going to relate the vaporization pressure to things like the heat of vaporization and a constant that's associated with each type of liquid and the temperature of the gas. This form of the equation is not as common as the next form we're going to see, but there are multiple ways to represent this equation, and you need to be at least aware of the fact that you can have more than one way to represent this information. So a couple of things we need to define here. Beta is the constant unique to each liquid. E, if you recall, is the base of the natural logarithm. Delta H vaporization we've talked about previously. R is the universal gas constant. You want to make sure that you choose the correct gas constant. So you might be like, well, wait a minute, Corin, isn't there a gas constant that's like 0.08206 liters atmospheres per mole Kelvin? You are correct. But in this case, we actually need to use a different gas constant. That was the gas constant that we typically used with our ideal gas laws. In this case, we need to use the universal gas constant in joules per mole Kelvin. And then temperature is the Kelvin temperature of the gas. One of the most common errors that I saw on exam 2 was that folks forgot to convert degrees Celsius to Kelvin. And in general, especially for thermochemistry problems, you're going to want to convert to Kelvin when you're solving for these types of problems. So it's super important that you do that conversion. If you're like, hey, wait, how do I do that again? Remember, Kelvin is where you add 273, sometimes it's 273.15, depending upon the number of significant figures, to your degrees Celsius. So if I wanted to convert degrees Celsius, say for example, if I had 25 degrees Celsius, then I would add 273.15, and that would give me 298.15 degrees Kelvin. Okay. So this is the form of the equation that you are going to be using most commonly. This is what they call a 2-point form because it's actually measuring two different pressures and two different temperatures. So say for example, I measure T1 and P1, and then I measure again and I get T2 and P2. That's how I'm going to be able to plug in two different sets of values for this equation. So let's take a look at an example of what solving this type of problem would be like. So before we move on, I want to make sure that you have the opportunity to write down this equation in your notes because it's going to be something we're going to use for the next type of example problem. Okay, so here's an example of what that type of problem would look like. Propane has a normal boiling point of negative 42.0 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What is the P vaporization, or the pressure of vaporization, of propane at 25 degrees Celsius? So notice here, I have my P1, so it says at a normal boiling point. Well, we know that normal boiling point means a pressure of 1 atmosphere. They give me T1, this is a temperature, and they give me my heat of vaporization. And then they're asking for P2, this is my P vaporization. So they're asking for P2 of propane at T2, 25 degrees Celsius. So let's take a moment and write down your givens. What is all of the information that you are given in that problem? And if you're not certain, that's okay. Just start out by writing what you know. So let's take a moment and write down the information that we're given. So we're given P1. We're given T1. We're given our delta H of vaporization. We're solving for P2, that's our unknown. And we're given T2 is equal to 25 degrees Celsius. So hopefully in your notes or on your whiteboard, you have something that looks like this. Notice you're going to need to convert both of your temperatures to Kelvin. Remember, you do that by adding 273.15 to whatever the temperature in degrees Celsius is that you're given. Now that we have this information, we have all of our givens, now we can think about substituting and solving for P2. We have to do a little bit of simplification. So in this case, right, P2 is measured in atmospheres over 1 atmosphere. That's going to cancel. And so all I'm going to have is the natural log of P2. So the original equation has P2 over P1. But in this case, because I'm substituting P1 as 1 atmosphere, and any number over 1 is that number, then I can simplify this expression so that it's just the natural log of P2. So now my equation simplifies, and I have the natural log of P2 is equal to negative delta H of vaporization divided by R times 1 over T2 minus 1 over T1. So if you're thinking about writing out this expression, it's super helpful, I think, to write out the given equation and then simplify and rearrange for what you're solving for. That will make your life easier in the long run. So go ahead and rearrange your equation. In this case, we're solving for P2. So then the only thing that we have to do here is substitute in our values that are given. So we're solving for the natural log of P2. We're given our delta H value. That's 19.04 times 10 to the third. Notice the units here. This is joules per mole divided by our universal gas law constant, 8.314, again, joules per mole Kelvin. Interestingly, right, because this is in the denominator of a denominator, because of the reciprocal relationship, it's going to come up and be Kelvin, but the rest of the units will cancel. So my joules per mole will cancel with my joules per mole. And then I'll have Kelvin in the numerator. So whatever number I'm solving for here, right, I'm going to solve and then apply that, right, to what's in my parentheses. So I'm going to solve for what's in my parentheses. I'm going to solve for what's outside my parentheses and then multiply them together. So go ahead and take a moment and with your calculator, check to make sure that you get the value of 2.226 when you substitute the information here and solve. If you need to solve it in steps, that's okay. You remember you're always going to solve what's in your parentheses first. So subtract 1 over 298.15. So this value solve and then subtract 1 over 231.15 from it. Solve for that first. Then you're going to multiply your numerators together and divide by your gas law. So double check, make sure your math makes sense. If you're like, oh, I trust you, never trust me. It's always better to check my math in a calculator. Never hurts to double check your calculation because sometimes you just input the information incorrectly. It's always better to double check. Make sure. One of the tips or tricks that I use is I use more parentheses than I need to, and that will typically prevent me from making a calculator error. Okay, so I double checked my math on my calculator and I did get 2.226. Remember, I have this negative sign for a reason. It should cancel with the negative that results from this equation. So I should have a positive number here. It should be a positive number. Then, in order to cancel my natural log, I have to do e to the value. Right? So e to both sides is going to cancel my natural log, and so I'm left with P2. E to the value of 2.226. Double check my calculator math. And I get 9.2627. And in this case, if I think about the numbers that I started with, right, my number of significant figures, let's go back and double check. So it looks like for the information that I'm given in the problem, 3 sig figs is what I'm looking for. So because this is an inferred value, right, 1.00 ATM would be the same, right? So I'm using 3 sig figs for my solution. So my pressure is 9.26 atmospheres. This is the reason why they have the symbol of danger on propane cylinders. Ooh, the heat of vaporization. Do you notice that the value that we were given in the problem was in kilojoules? Notice here, this is kilojoules per mole, but in order to be able to cancel my units, I have to convert my kilojoules to joules per mole. The reason for using the 2-point equation is because we're given two sets of values. So it's easier to solve this problem with a 2-point equation because we're actually looking at a change, in this case, a change in temperature and pressure. So a couple of quick key points. Natalia asked a great question. You have to make sure that you convert your kilojoules to joules. That's because I need my units here to cancel, and they both have to be in joules in order for that to happen. And then Brenda asked a great question about which equation you would choose to use. So if ever you're given a problem where you're given two sets of information, so if you're given two temperatures or two pressures and a heat of vaporization, you're going to want to use this equation, the 2-point form example. So you've probably seen the gas cylinders, say for example, for a grill or maybe for a stove, and they always have this symbol on them. And the reason for that is, if you think about it, the pressure for propane, even at 25 degrees Celsius or room temperature, is 9.26 atmospheres. Right? So that's a lot of pressure for this gas. So that's the reason why we always have to be careful around propane gas. A really common and practical example of the way delta H of vaporization relates to life. Okay, so let's take a minute and recap. What do we know so far? We've covered a little bit of information today. We want to make sure that we're carrying all that with us as we move forward. So we've talked about equilibrium vapor pressure. This is the pressure of a vapor in equilibrium with its liquid phase. It's going to depend on temperature, and it's going to depend on my delta H of vaporization and my intermolecular forces. So the pressure of a vapor in equilibrium with its liquid phase, and it's dependent upon temperature, delta H, and our intermolecular forces. We talked a little bit about boiling point. So boiling is when the vapor pressure equals the external pressure. And we know that normal boiling point occurs when our vapor pressure is 1 atmosphere. And then we used our Clausius-Clapeyron equation to see the relationship between the pressure of vaporization and temperature. Now, if I go back, right, I want you to see a couple of things that we looked for in this type of problem before we move forward. When we're solving this type of problem, we're going to make sure that we identify the givens in the problem. Sometimes those givens are actually hidden in words. So we have to make meaning out of, say, for example, normal boiling point and know that that means 1 atmosphere. We're also given information in the problem that might require a conversion or dimensional analysis. So we're given temperatures in degrees Celsius, but we know that we have to convert those degrees Celsius to Kelvin. And we're also given our delta H of vaporization. That's most commonly given in kilojoules per mole. But we know that when we solve this problem, one of the things we will need to do is convert our kilojoules per mole to joules per mole in order to be able to substitute and solve. There's some basic math that we need to do to rearrange, right, and substitute to then have the most ideal form of the equation to plug our numbers into. This is something that can be done by substituting in our numbers as given and then seeing that in fact this cancels to simplify. So we have the natural log of P2 by itself because P1 is just 1 atmosphere. So here's the really cool part about solving these types of problems. You're remembering specific information, you're applying concepts, for example, like being able to convert degrees Celsius to Kelvin, or concepts like converting kilojoules to joules. Then, in order to solve the problem, you're going to have to do some analysis or some math manipulation. That requires that you know how to resolve the natural log, and you do that by using the e function. So e to the natural log, e to the 2.226 is how we get P2 by itself. Those are all skills that are associated with solving this type of problem. And there's a process that you use. Typically, that process begins with writing out your givens and then rearranging your equation, then substituting in your values, and then doing the actual calculation. That kind of 4-step procedure is a general approach to most problems like this that will work. Okay, so we know conceptually the pieces that we're doing. We're connecting our equilibrium vapor pressure to boiling point, and we're thinking about how that vapor pressure and temperature are related. So now we're going to take a look at heating curves. So heating curves are what allow us to visualize the transfer of heat. So when I warm a substance or cool a substance, and it changes phase. So a heating curve is going to help us to see that. It's the heat of changing the temperature of a solid, a liquid, or a gas. And if you recall, we actually have an equation for that we're already familiar with. We know the equation Q is equal to the mass times the specific heat in joules per gram degree Celsius times our change in temperature. So this is something that you saw on exam 2 that's coming back around and will be relevant for the exam 3 and for our final exam. The heat then of this phase change is described by the delta H of whatever that phase change is. So Q, or the heat, is equal to the number of phase changes that occur. So for example, if I go from solid to liquid to gas, right, I've got 2 phase changes that are occurring. The phase change from solid to liquid, and then the phase change from liquid to gas. So the heat is going to be something that is cumulative over all of those. So here's an example of a heating curve and what that looks like. Interestingly, we often only look at a part of a heating curve. We don't necessarily always look at the whole heating curve, but in this case, we're going to talk through it so that you're familiar with the entirety of the heating curve before we zoom in and look at a specific section of that heating curve. Notice the axes of my diagram. I've got energy as my x-axis, and I've got temperature as my y-axis. So here, if I see an increase in my slope, that means that as I put energy into a solid, my temperature is increasing. It's going to increase until I get to a point. This point is when my solid begins to become a liquid, and it's going to stay at that temperature until all of my solid has become a liquid. Then my temperature is going to increase again. So as I put more energy in, here notice my temperature is constant even though I'm putting energy in. Whereas here I'm putting energy in and my temperature is increasing. It's going to increase until I reach this point where now my liquid starts to become a gas. And so I'm going to, again, continue to put energy in, but my temperature is going to be constant as all of my liquid molecules become gas molecules until I reach this point. At this point, all of my liquid molecules have become gas molecules, and now I put energy in and my temperature increases for my gas molecules. So we're going to take this apart and look at a couple of features of this heating curve. So the melting point is the temperature at which my solid starts to become a liquid. You can typically measure melting point for most solids, so you can heat them and observe the point at which the solid becomes a liquid. That's what's referred to as the melting point, and it has a specific temperature associated with materials. Now, sometimes that temperature is reported in a range. That's usually because our materials, right, if we're studying a specific chemical, aren't always pure, and so sometimes there can be something else in the material that can cause it to melt at a different rate. But melting point is a property of solids. the property of liquids that we were just talking about is boiling point. So this is the point at which a liquid starts to become a gas. You're probably familiar with the boiling point of water, for example. There are equations that govern the heat associated with this transition. So for example, when we think about a solid melting, we're going to use Q is equal to the mass of that solid times the specific heat of that solid times the change in temperature. If we're thinking about the heat that goes into fusion, where a solid becomes a liquid, we're going to use the equation Q is equal to N, or the number of moles, times the delta H. Remember, delta H is always in kilojoules per mole. So our moles cancel, and this gives us kilojoules. If I'm looking at, right, the energy that's going into, or the heat that's going into a liquid, this again is the same form of the equation. It's just in this case, instead of being a solid, as we see here, my specific heat is now for a liquid. Say, for example, the specific heat of water is 4.184 joules per gram degrees Celsius. That's something you can find on your equation sheet. We've used that value before when we've solved different types of problems. And again, right, if we're thinking about this Q, oh, that should be a heat fusion. Let's fix that. And then in this case, it's not fusion. I'll have to find another equation. In this case, what would the transition be from liquid to gas? Do you remember? Going from a liquid to gas would be the delta H of vaporization. So this guy should be Q is equal to, I don't want it to, there we go. Q is equal to N, and then we've got our delta H of vaporization. And I'll go in and fix that, right? So it's important, right? The reason why I included this is so that you notice this is N times your delta H. This is your delta H of vaporization. Notice these are your Q's associated with the transitions, right? Where I'm putting energy in, but I'm not actually changing phase, right? So there's no transition that's occurring here. I'm just putting energy in and it's still solid. So my solid stays a solid and I'm putting energy in. Whereas my Q values, those are going to change, right, when I have the transition. Okay. All right, so let's fix this guy. I'll put in our delta H of vaporization. That's what goes here. So notice here are the negative values of going from a gas to a liquid, or going from a liquid to a solid. So this is an example of a complete heating curve. Let's take a look at how we might use this heating curve to be able to then solve a problem like a Clausius-Clapeyron equation. So how much heat is required to completely melt a 25-gram block of ice initially at negative 20 degrees Celsius? So before we can solve the Clausius-Clapeyron types of equations, we've got to think about how we can cumulatively account for the heat. So we have the specific heat of ice. That's going to be a value that's given to you, not something you have to memorize. And again, you're going to be given a delta H of fusion. Remember, right? What does fusion mean? Right? That's a solid going to a liquid. And then we have our Q1. So this is the specific heat of ice and the change in temperature and the mass of that. And we have our Q2. This is the number of moles and our heat of fusion. And so our Q total is when we're adding up each of those Qs. So I'm going to take a moment and give you the opportunity to write out this example in your notes. Notice our temperature initial is negative 20 degrees. our temperature final is 0 degrees. Remember, right, for this, we don't have to convert to Kelvin because our specific heat is in joules per gram degree Celsius. So for right now, we'll just leave these temperatures as they are. So there's a lot that's going on here. So we have our Q1, which is our mass times our specific heat of the ice and our change in temperature. So I have 25 grams. That was what the information that was given in the problem. I have my specific heat of my ice, and I have my temperature change. So I'm going to multiply those together, right? Remember this 1 joule per gram degree Celsius, right? And converting between joules, 10 to the third joules, is useful, right? Because I want to be able to tell the difference between kilojoules and joules. So when I do that calculation, I should result with 1.045 kilojoules. So let's double check our math. This is in joules, so I have to convert. So I've got 1,045 joules, but I need to convert that to kilojoules, so I'm going to divide by 1,000. And I get 1.045 kilojoules. Okay, so that's Q1. If you're thinking about Q1, that's what's occurring here. That's when I'm in my solid phase, right? My Q2 is my heat of fusion. So if I think about this, right, that's just here. So from this point forward. Okay, so let's look at Q2. This is my N times my delta H fusion. So I have 25 grams. I'm going to be able to convert that, right, to moles. So I have 18.02 grams is 1 mole. And I have my 6.02 kilojoules per mole. Oh, looks like it's shifted. I'll have to fix that so my moles come over. So if I think about that, right, I have 25 times 6.02, 150. I divide by 18.02, and I get 8.35 kilojoules. Notice here I don't have to do any conversion because I'm already in kilojoules per mole. I'll fix this. The 18.02 should shift and be over here. The kilojoules per mole should be here. Notice you can cancel your units to check and make sure that you set everything up correctly. So now I'm going to add to get my total Q. I have my 1.045 kilojoules, right? That's from when I'm as a solid and putting heat in. And then I have my Q2. This is when I'm going from a solid to a liquid. That's my 8.352 kilojoules. And so my total then ends up being 9.4 kilojoules. So that's the total amount of heat, right, that is necessary to completely melt a 25-gram block of ice initially at negative 20 degrees Celsius. So if you think about it, I'm going from a solid to the melting point, then from my melting point to a liquid. This calculation, the first calculation is going to put heat into the ice until it gets to its melting point. So until it gets to right here. Then I'm going from my melting point to a liquid. That's the second calculation, or Q2. My total heat then, because remember Q is heat, is adding Q1 and Q2. Okay, so that's an example of the phase transition heat calculations that you'll be doing. Let's talk about critical point. So what happens if you keep increasing the temperature of a liquid and it's vapor in a sealed container? Right? Caveat, that's if the container doesn't explode. So that's if you have a container that's strong enough that it can endure the pressure. So at a high enough temperature and pressure, separate liquid and gas states no longer exist. So above the critical temperature and the critical pressure, there are only what they call supercritical fluids. This is a fascinating area of study. Their properties are really unique. I'll see if I can find a video to send out with my recap for this week of supercritical CO2. There's a really cool one, but the video that I had looked for no longer exists. So I'll also have to see if I can find an alternate one. So the critical or supercritical fluids live in the upper right-hand corner of your phase diagrams. So a phase diagram really shows you the points of transition. So a heating curve tells you at what temperature and pressure you're going to see that transition. So phase diagrams help you to see all of the phases at once. So notice our pressure here is in torr, and there's a really important caveat. It says the pressure is not to scale. And again, it has temperature, and temperature is not to scale here. Sometimes that's necessary if you're going to be able to see all of it on a single diagram. So notice here, this is where my molecules exist as a solid. And you're going to notice that as the pressure increases, right, they could transition from a solid to a gas. Here is where my molecules exist as a liquid. Notice this is the vaporization curve, right? At a specific temperature and pressure, I could transition between a liquid and a gas. But the triple point is the cool part on this diagram. So the triple point is the temperature and pressure where all three phases are in equilibrium. So if you could look at this and physically see it, you would literally see the molecules exchanging between being a solid, a liquid, and a gas, all at the same rates. That's really cool. Here's the reason why. So when we navigate, say, for example, the phase diagram for water, let's say we're looking at 1 atmosphere of pressure. And we want to know what's the temperature then at which we would see a liquid then go to a gas. So let's say I follow 1 atmosphere out, right? So this is the pressure of my liquid. And I'm going down and I'm saying, oh, at 25 degrees Celsius, at 1 atmosphere, I'm a liquid. When, right, I change my pressure. So let's say I reduce my pressure down to 0.006 atmospheres. And I go across. At 0.01 degrees Celsius, my solid, liquid, and gas all exist in equal rates. If I wanted to figure out the pressure at which I would convert a liquid to a gas at 25 degrees Celsius, I could read across and find where that temperature is to be able to figure out the pressure. So if you're given a temperature, you can find the pressure at which a substance, say for example, is a gas. Or given a temperature, you can find the pressure at which a substance is a liquid. Or given a temperature and a pressure, you could determine if it's a solid, liquid, or a gas. So phase diagrams are really cool in that they allow you to be able to determine what physical state your material is in. So here's an example. Here's carbon dioxide. You've probably seen this. It's often used, say, for example, as smoke for special events. Sometimes it's used to make ice cream. But here is the phase diagram for carbon dioxide. It actually is also a supercritical fluid. And you can see here, right, its triple point is negative 56.4 degrees Celsius and 5.11 atmospheres. If you wanted to know the transition at which, right, it would go from a liquid to a gas, right, that occurs at 73 atmospheres and 31.1 degrees Celsius. So that's the reason why it generates that really incredible smoke effect, is because it's literally the solid, in this case, becoming a gas. So that's why this curve here is so low, right? It's a solid, but it can pretty easily become a gas. All right, so we're going to do one more Clausius Clapeyron, and then we're done for today. So I have an open container of mercury in a room at 25 degrees Celsius. So at what temperature will the vapor pressure of the mercury be tripled? Enthalpy of vaporization for mercury is 59.11 kilojoules per mole. So this is an example of a Clausius-Clapeyron equation that pulls all of the information together. So the first thing I'm going to do is identify some of the information in the problem that's given. So I have a temperature, right? Notice this is T2, right? My T1 is 25 degrees Celsius. So that's two pieces of information I'm going to pull out from this problem. Because I have two temperatures, I know that I'm going to use the 2-point form of the equation for Clausius-Clapeyron. This is the question that Brenda asked that was so astute. She was like, how do you know when to use which form of the equation? Well, if you're given two temperatures, then you know that you have to use this form of the equation. Remember, anytime we're using the Clausius-Clapeyron equation, we're going to be converting our temperatures in degrees Celsius to Kelvin. Now, in this case, the problem is asking for us to find the vapor pressure. So we're going to say, hey, we're looking for, right, P1. And in this case, our P2 is when P1 is tripled. So there's a specific relationship that the problem describes between P1 and P2. So T2 is what we're looking for. We're going to represent our pressures just as the variable P1. So let's think about how we can simplify our problem then. We have 3 times P1 over P1. Notice our P1s cancel, right? So all we're left with is the number 3. And so it's just the natural log of 3 on the left-hand side of this equation. So again, we're simplifying our equation so that we can solve for, in this case, T2. So we have to do a little bit of rearranging in order to be able to isolate or solve for 1 over T2. So this is what that algebraic manipulation looks like. I'm going to start from my generic form of my Clausius-Clapeyron equation. I'm going to isolate my terms. So that means I'm going to multiply my delta H of vaporization and R. I'm going to multiply it by its reciprocal. So if I multiply both sides by R over negative delta H of vaporization, I can move this term to the left-hand side of the equation. So that's what you see right here. I'm multiplying both sides of the equation by the reciprocal of the term that you see in the red box. So the reciprocal would be R over negative delta H of vaporization. Then I'm going to isolate my 1 over T term. So I want to get 1 over T2 by itself. That means I'm going to add plus 1 over T1 to both sides, which is how I get to this term. Notice 1 over T2 is what I want because I want to get T2 by itself. So I'm going to step back through that to make sure that everyone's on the same page. My algebraic manipulation is I'm multiplying by the reciprocal of the term that's in the box. The word reciprocal just means that I've flipped the numerator and the denominator. So in this case, I'm multiplying both sides by R divided by negative delta H of vaporization. Once I've multiplied both sides by R over delta H of vaporization, notice I still have my negative term. Then I need to get my T2 term by itself. So in order to do that, I'm going to add 1 over T1 to both sides. That gives me my final overall equation. Once I have my equation and I've isolated for T2, then I'm going to substitute and solve. So remember, negative natural log of 3, because I've simplified with respect to my pressure. This is my gas constant, so 8.314 joules per mole Kelvin, divided by my enthalpy of vaporization, so 59.11 times 10 to the third joules per mole. And then remember, you want to make sure that this is T1, so that's 1 over 298.15 Kelvin. notice my joules cancel, my moles cancel, but my unit for Kelvin should be K negative 1, which is good, right? Because this is the term 1 over T2. So in order, right, to get T2, I have to divide, right? So I have to divide 1 by this value. So if I want to figure out what T2 is, I'm going to divide 1 by 0.00319. So 1 divided by 0.003199 is going to give me 312.6 Kelvin, or if I subtract 273.15, 39.4 degrees Celsius. So here's what's really cool about this problem. The vapor pressure of mercury triples with only a 14.4 degree temperature increase. So that's such a tiny change in temperature, but a huge change in vapor pressure. Okay. If you want some additional help solving problems like this, I highly recommend that you check out discussion section tomorrow. Going to be really useful because we're going to start thinking about phase diagrams and making sense of heating curves and doing delta H vaporization calculations, as well as the Clausius-Clapeyron equation. Ooh, that's a mouthful. For some reason, I'm getting jumbled up over my words. Quick question from folks. They said, hey, can we attend a different discussion section? Yes, you can always attend more than one. You can come to multiples. You are always welcome. Essentially, the invitation will be to all for any. So Arlene has been really gracious in terms of being willing to allow folks to attend the 4 o'clock session if that's not one that they're regularly scheduled for. And that's true for the 8 a.m. and the 3 p.m. sessions of discussion as well for me. So essentially come to the discussion section that works best for you, and then you can work through as many problems as you like. And if you have questions about lab or Alex, we can do those then too. Last piece of information. Next week is exam 3, and then we're going to be reviewing for the final. I'll send out information when I send out the review and recap email for this week about signing up for exam 3. So I'll stay and hang out if you have any questions. Otherwise, I will